So we are looking at, for Chapter 2, Video 2, an acid and its conjugate base, the acid being water and the conjugate base hydroxide, and the base and its conjugate acid, with our base as ammonia and our conjugate acid ammonium ion. The difference is going to be shown by molecular formula. So the difference between a conjugate base and a conjugate acid is its molecular formula. An acid has one more hydrogen ion or hydrogen atom than the conjugate base. The acid will also differ from the conjugate base by a charge of 1, with the acid being more positive in charge than the conjugate base. When your molecule has more than one proton, you decide which proton is the acid proton by determining which proton has the lowest pKa. For our acid H2O, it has 2 protons, but they are equivalent because they have the same connectivity. Ammonia, as a conjugate base, has a conjugate acid ammonium ion, and so ammonium ion as the acid should have one more proton than ammonia, the base. It also, when the base is neutral, when the conjugate base is neutral, the conjugate acid should be positively charged. So notice that ammonia, NH3, has 0 charge, and ammonium ion is charge of positive 1. Water is the acid. It has one more proton than hydroxide ion. And when the acid is of neutral charge, it should have one more charge than the hydroxide ion, and so hydroxide has a negative charge. Acids have different strengths. We can look at the acid strength here. We have HCl is a strong acid, and you should have learned in Gen Chem what weak acids and strong acids are, and you should remember that from Gen Chem. Hydrogen chloride or hydrochloric acid, as a strong acid, should dissociate fully, and it has a pKa, I think, of -6 or -7, a very low pKa. And when we identify the acid in the reactants, we should be able to identify the base in the products as having one less hydrogen, so that's chloride ion. When we look at the reaction arrows, the reaction arrow indicates what is the favored side of the reactants or the product, and we can determine what is favored, reactants or product, by analyzing pKa. The side of the reaction that has the acid with the greatest pKa is the side of the reaction that is favored. So we identified HCl as the acid, its conjugate base is chloride ion, and H2O is the base in the reactants, and H3O plus is the acid in the reactants. H3O plus in the products has a pKa of -1. Because the -1 is greater than -3, the reaction goes towards the higher pKa and favors products as at equilibrium for this reaction. If we look at the second reaction and determine which side of the reaction is favored, we look at acetic acid. It has a pKa of approximately 5, has one more hydrogen ion than its conjugate base, acetate ion. Our base in the reactants is water, and its conjugate acid in the products is H3O plus. All reactants will always have an acid and a base, and products will always have a base. When we have an acid-base reaction, the reactants will have an acid and a base, and the products will have an acid and a base. And we can determine what side of the reaction is favored by which of the acids, the product acid or the reactant acid, has the lowest pKa. Because acetic acid has a higher pKa than H3O plus, the higher pKa side of the reaction is favored at equilibrium, and this reaction, as written, equilibrium will favor reactants. We are looking at the acid dissociation constant here. This is something that you should remember from Gen Chem. I'm not going to ask you to do calculations of acid dissociation constants. We can take Ka and relate it to Keq. We should remember that H3O plus is acid, A minus is the conjugate base, and HA is the conjugate acid of a conjugate acid-base pair. So for acid strength, very strong acids have a pKa of less than 1. Moderately strong acids have a pKa of 1 to 3. Weak acids have a pKa of 3 to 5. Very weak acids have a pKa of 5 to 15. And extremely weak acids have a pKa of greater than 15. The stronger the acid, the larger the Ka, but the stronger the acid, the smaller the pKa. pKa follows the same trend as pH. As pH decreases, the solution becomes more acidic. As pKa decreases, the solution is more acidic. We should remember that pH is the negative log of H+, and so pKa is the negative log of Ka. And remember your rules about conjugate acid-base pairs and your rules about acids and bases. The stronger the conjugate acid, the weaker the conjugate base. That is a very important rule, and many of you remember it from Gen Chem. The stronger the conjugate acid, the weaker the conjugate base. For pH, pH is the negative log of H+ concentration, and so it's a measure of how much H+ is present. When pH is very low, the concentration of H+ is very high. For a pH of 14, that is equivalent to 10 to the negative 14th, and so that's indicative that pH is very low. And for a pH of 0, that is equivalent of 10 to the 0 or 1, and that is in saying that the concentration of H is much greater than 10 to the negative 14th. Okay, so at pH of 14, the concentration of H+ is 10 to the negative 14th. which would give us 13 zeros and then a 1. You should know, you don't have to memorize the approximate pH of any of the substances on this. This is just a chart to give you an idea of where different things fall in terms of acidity. A lot of people like to look at the biological fluids and their acidity. The most significant of the biological fluids that I like to remember is blood with the pH of 7.4. Okay, carboxylic acids are the most common organic acids. And we are going to be dealing with these a lot, and you have your functional group chart, and I gave carboxylic acids on the functional group chart. The carboxylic acid portion of this molecule is highlighted in the yellow square in this slide, and acetic acid has a pKa of 4.76, formic acid of 3.75. Most carboxylic acids are on the range of 4 to 5 for their pH. The acid proton here is the proton connected to oxygen, which is not carbon or hydrogen, and so can be defined as a heteroatom. And this proton has the weakest bond. It is the most easy to break. So we can say that pKa is a measure of how weak the bond from the to hydrogen is. I have a chart of pKa's that you should fill out as we go through and look at the pKa of these different functional groups listed in the middle column. Protonated carboxylic acids, protonated alcohols. These are all functional group names that you're going to see in the next several slides. And we'll fill out a few together, but then I expect you to fill in the rest. So we have methanol and ethyl alcohol, methyl alcohol and ethyl alcohol, with the acid proton being the proton connected to oxygen. And we can draw this out in the chart. So let's draw out only the acid proton as red, so that you know which proton has the pKa given. This pKa of the alcohol proton is approximately 16. For amines, the pKa of the proton bonded to nitrogen is approximately 40, 35 to 40. And so that's a very high pKa. Remember, strong acid, low pKa, weak base. So if we have a pKa that is high, then that's a weak acid, but the conjugate base will be stronger. So drawing it out in the chart is given. Then we go to protonated amines. We have protonated methylamine. So this is just an amine that has one more hydrogen than methylamine. So we call it protonated because it has added a hydrogen. So now the lone pair that was on the nitrogen previously is bonded to a hydrogen. And what that does is that pKa is now 10.7 or 11 because a charged atom is going to have a weaker bond because there's a lower electron density. So if we draw in protonated amine into your chart, that's approximately 11. For myself, I memorize these pKa's because we have to rank the acid strength or the base strength a lot. And if you remember the pKa's of the different types of functional groups, you'll have an easier time ranking what is the strongest or weakest base. When you do this chart, you should go back to the chart and put a positive charge on the nitrogen here, it has 4 bonds and should have a positive charge. Okay, protonated alcohols. And protonated carboxylic acids. This is showing you where the protonated hydrogen atom is located. It's an additional atom connected to the alcohol oxygen. This is whenever we have a charged atom to hydrogen bond, we're going to have a lower pKa. Protonated alcohols have a pKa that is less than 1, around -2 to -3. And so that is now in the strong acid category. So we've drawn it in your chart so you know what that looks like. And we don't forget the positive charge. Well, not on this one. We did on the nitrogen one. Okay, so protonated acetic acid, the hydrogen is connected to the carboxylic acid oxygen that is double bonded. This has a much lower pKa of -6. So if you recall, alcohols that are not protonated are 16, and carboxylic acids that don't have the additional proton are 3 to 5. So what you're going to do then is note that when you have a normal carboxylic acid versus a protonated acid, that the pKa is always going to be lower for the protonated form, but that the order of pKa between functional groups is still consistent, because the non-protonated alcohol is 16 and the non-protonated carboxylic acid is 4 to 5. The carboxylic acid is already more acidic than alcohols, so it makes sense that adding a proton and still having a similar structure, the protonated form of the carboxylic acid is more acidic than the protonated form of the alcohol. I'm going to let you guys draw the carboxylic acid functional group into your chart on your own. As we go through the PowerPoint, you'll see each of these different type of molecules: carboxylic acids, protonated carboxylic acids, water, alkynes, alkenes, and alkanes, and the pKa is given here. And so I recommend that you simply fill in the chart, giving the basic structure and drawing which hydrogen is being discussed as the acidic proton in red. So moving forward then, we have alcohols behaving as an acid or an alcohol behaving as a base. This is because of the lone pairs. So we'll define Lewis acid is defined as a Lewis electron acceptor, and a Lewis base, you should have learned in Gen Chem, is defined as a Lewis electron donor. So we call an electron acceptor an electrophile, an electron lover, and a base is called as an electron donor is called a nucleophile or a nucleus lover. So those electrons that are donated by the base are attracted to a positive charge, which occurs at the nucleus. So remembering our Latin roots, phile meaning love, that helps us remember our definitions. Electrophile, electron lover, nucleus, nucleus lover. So just quickly here, we have that when we have an acid, we have to have a positive charge. So the oxygen to hydrogen bond is a polar bond, with oxygen being a more electronegative atom. And so if you draw your dipole, you have that hydrogen is partially positive and oxygen is partially negative. So the base, we have acid and base, just as we always have. Our base is our electron donor. A lone pair from the hydroxide ion is going to make a bond to the hydrogen. What are the characteristics of this electrophile? An electrophile can be identified by certain characteristics, and we will discuss those characteristics on another slide. But in this case, we have the electrons from hydroxide being donated to make a bond to the partially positive hydrogen. So hydrogen is accepting electrons from the oxygen, and then the bond that hydrogen previously had to oxygen is breaking. It's a weak bond. And so then those electrons are going to the oxygen bonded to the methyl group. Okay, this gives us methoxide and water. So this is an acid-base reaction. The acid changes by molecular formula by one hydrogen. So these are our conjugate acid-base pair. Here's our conjugate acid and our conjugate base. The hydroxide ion is our base. It differs by one proton from its conjugate acid, water. And we have a neutral acid going to a charged negative base, and a negative base going to a neutral acid. In order to act as a base, you have to be able to donate electrons. So because methanol has a lone pair, it can donate those electrons and act as a base. So methanol can act as an acid or a base. In this case, we have an electron pair being donated to make a bond to this partially positive hydrogen of water. Now, I highly recommend that you draw your dipoles on your acid. If you draw in the dipoles on your acid, you will see by dipoles that oxygen should have more electron density than hydrogen because it's more electronegative. So ignore formal charge when you are determining what your electrophile or electron lover is. Formal charge doesn't tell the whole story. In order to know where electron density exists, you have to draw the dipoles. Okay, so we are going to take a break and define electrophiles and nucleophiles. And then in the next slide, we will go on, or in video 3, we will go on to talk about more about Lewis acids and Lewis bases in the way that the base is donating a pair of electrons and the acid is accepting a pair of electrons. But it will be helpful to look at these definitions so that we can get used to identifying what are the characteristics of an electrophile, how do I know what's going to be the electrophile, and what are the characteristics of a nucleophile, and how can I identify a nucleophile? Or how can I identify a Lewis acid, and how can I identify a Lewis base? All right. So we have that a Lewis acid is an electron acceptor, aka an electrophile, electron lover. And the characteristics of an electrophile are these three things. It doesn't have to have all three characteristics. It only has to have one of them to be an electrophile. And so one of these three characteristics makes an electrophile. Either the atom has a positive charge, the atom has a partial positive charge, or the atom has an incomplete octet. When we look at positive charge, that's easy as long as formal charge is given. For example, methyl cation is an electrophile. For a partial positive charge, our example is the acetone, which has a dipole because oxygen is more electronegative than carbon. So the carbon has a partial positive charge and can act as an electrophile. And for incomplete octet, these are going to be the atoms in group 3. That's our primary example. And the one that we will most commonly encounter is boron. This has an incomplete octet. It doesn't obey the octet rule. So let's talk about Lewis base. Lewis base is an electron donor, aka a nucleophile. It loves the nucleus, loves positive charge. So electrons are attracted to positive charge. But how can we identify a nucleophile? Nucleophile has to have one of these three characteristics. It must have a negative charge, a pi bond, or a lone pair. Wasn't done with that. All right, pause. So for Lewis base, one of these three characteristics, either the atom that is acting as the electron donor will have a negative charge, it will be part of a pi bond, or it could have a lone pair. So what this means is that we need electrons that are not in a sigma bond in order to have electrons that can be donated. Okay, so we can see these electrons by looking at atoms that have negative charge, pi bond, or lone pair. And we can go back to the previous slide and look at our methanol acting as a base. What is the characteristic that makes it a base? It has a lone pair. And so we can identify that it can act as a base. But how can you decide when it's going to act as an acid and when it's going to act as a base? Well, this is going to be dependent on the pKa of the two different reactants. In the reactants, the substance that has the highest pKa will act as the base, and the substance that has the lowest pKa will act as an acid. And this concept is going to be covered in a later part of chapter 2. All right, so that's the end of this video.